Okay, just like a normal SI session where we spend the first half going through the problems on our own and the second half doing them together, I want to try and model that with this virtual way of conducting this session. So hopefully by the time you're watching this video, you've already gone through the PDF of the problems and gotten some practice on your own, and now we can come together and get some clarification. As you've heard me say a million times, the primary purpose of the practice problems is to identify what you know and what you don't know. It's most important to know what you don't know so that you can practice it before the day of the exam. The secondary purpose is to get practice and become more confident in your ability to win the question every time. That being said, I think the best use of your time is to do Dr. Scott's exam review. He wrote he wrote the exam and he wrote the review. So that means the questions on the review will be most similar to the content on the exam. So that's going to be your highest yield study time. Hopefully this is also helpful answering some more questions and getting some more practice. Because you've already gone through the problems and identified your questions, there's not going to be any Dora the Explorer moments on this review where I stop and say, type this in your calculator, see what you get, or think about what this could mean. We're just going to go through the problems and get some clarification. So that being said, let's jump into these. What amount of 1.2 molar potassium phosphide solution contains 81.4 grams of potassium ions? Well, the first thing I want to make sure that I recognize is that this big capital M, molar, means moles per liter. I also want to recognize what potassium phosphide is. I might be tempted to think phosphide. I need to flip over my periodic table and look at the polyatomic ions, see what this looks like and what charge it has. But we'll remember that this "ide" tells us that this is just a phosphorus ion, and this is potassium. Based off the position on the periodic table, potassium has a plus charge and phosphorus has a 3 minus. So that means potassium phosphide has 3 potassiums and 1 phosphorus. Once I've recognized those two things, we can solve the problem. Let's draw a long line, an equal sign, and establish where we're going. What amount of this solution? So we want to know an amount in liters. And we want to know, now that we know where we're going, let's identify where we're starting. There's only one number in the problem to start with, and that's 81.4 grams of potassium ions. From there, I can say that a gram of potassium ion goes to moles of potassium ions, and then moles of potassium ions to moles of potassium phosphide. And then this is the newest conversion factor, the newest concept, moles of potassium phosphide to liters of solution. Let's fill in the numbers here. 1 mole of potassium weighs 39 grams. For every 1 mole of potassium phosphide, we'll end up with 3 moles of potassium ions. That's what this 3 signifies to us. And because we have this moles per liter expression, we can say that there's 1.2 moles for every 1 liter. We're used to seeing moles on top of liters. Hopefully it still makes sense that we can have moles underneath liters as long as we make sure to put our numbers in the right spot. And if we run this through our calculator, we should get 0.58 liters. And we can double check our units, grams of potassium ions, grams, moles, 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 liters, liters. Great. The rest of the problems I generated just by looking at the review and seeing what types of problems would be most helpful to go over. Problem 2 is straight from the ACS booklet. So it should feel like the ACS problems on the final, or very similar to the exam content. What is the maximum mass in grams of NO2 formed when 7.4 grams of N2O5 are consumed? It tells us the molar mass of our compounds we need to know, and it gives us this equation. We might be tempted to think that this equation is scary, but it's really our best friend because it's going to tell us the information we need to solve the problem. Same with these 2 molar masses we're given. So let's draw a long line and an equal sign. What are we trying to figure out? Where are we going? We're going to the maximum mass in grams of NO2. Great. And we're starting with 7.5 grams of N2O5. From here, we just need to get these units to those units. Grams of N2O5 becomes moles of N2O5. Moles of N2O5 can convert to moles of NO2. The only reason I can do this conversion factor is because I'm given this chemical equation. Moles of NO2 can go to grams of NO2. Let's make that O the right size. And because I wrote where I was going over here, I know that when I write this, it's time to stop. Lastly, we just fill in the numbers. It tells us that for every 1 mole of N2O5, there will be a mass of 108. And let's just do this other one. It gives us 46 grams for every 1 mole of NO2. This conversion factor here is that bad word, stoichiometry, and that tells us that for every 2 moles of N2O5, we'll end up with 4 moles of NO2. So when we're doing stoichiometry, or we need to get this moles to moles conversion factor, we're going to look at the equation and look at the coefficients. That's what gave us that 2 and that 4. Make sure our units are good. Grams, grams, moles, 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 grams, grams. Awesome. And when we type it into our calculator, we should get 6.39 grams. That makes sense, right? We started with 7.5. Some of the mass of that became this O2, and the remaining mass was the 6.39 grams of NO2. Great. Write the dissociation of the following compounds in water. Let's recognize here that we're dealing with an acid and a base. We know this is an acid because we have a polyatomic ion with a hydrogen attached to it. This acid is called perchlorate. So if I'm dissociating in water, I need to say plus, here let's just zoom in here, plus H2O. And then the next step, I need to know if I have a single arrow or the double equilibrium arrows. This acid is a strong acid, and that's something you're just going to have to memorize. One of the few things in the class that we just have to know. Strong acid gets a single arrow because it's going to dissociate completely, and we'll end up with ClO4 minus plus H3O plus. How do we know that? We know that because an acid is a proton donator. So we can think of this ClO4 being bonded to a hydrogen, and this H2O looks like this. But the ClO4 donated this hydrogen. It came over here. So now this ion has a positive charge, and this one has a negative charge. Hopefully that makes sense of what's happening in an acid. Here, we need to recognize that we have a nitrogenous base. We know that the nitrogenous bases are weak because Dr. Scott said that they would be. And so if we dissociate in water, we're saying plus H2O. Do I want a single arrow or a double arrow? It's weak. So I want these double equilibrium arrows to make it look better. If an acid is a proton donator, then a base is a proton acceptor. Maybe more accurate to draw the arrow towards the nitrogen. So we're going to end up with CH3, NH3. That 2 became a 3 because I added an extra hydrogen, and adding that positively charged hydrogen proton means I have a plus charge. This water was H2O, but we just donated one of the hydrogens, so it's OH minus. Okay, time to balance. Let's recognize what players we have in this equation. There is phosphorus, chlorine, hydrogen, and oxygen. One phosphorus over here, one over here. 5 chlorines over here and 1 over here. So let's throw a 5 there and get 5 chlorines on this side. Hydrogens, I have 2 hydrogens on one side and 8 on the other. 3 here and 5 here. 8 hydrogens, so let's put a 4 here to bring 8 hydrogens to this side. And lastly, oxygens. I have 4 oxygens on this side, and I have 4 oxygens on this side. 1, 1, 5, 5, 8, 8, 4, 4. Everything's balanced. Initially, when I did this problem, I went in this order: hydrogen, oxygen, phosphorus, chlorine. And it took a lot longer. So just recognize that there's not a specific order, but there is a way that will help you go faster. So as I was going through this way and balancing, it was just taking me a really long time. So I stopped doing that. I just decided to change the order I was balancing in, and it helped me to go faster. Maybe it's more helpful to just stick with what you're doing and solve it to the end. But as we get more practice, we might recognize, oh, there's probably a simpler way to balance this equation. Also remember that a multiple choice problem about balancing will probably just ask you, what is the coefficient on H3PO4 in the balanced equation? You need to balance the equation all the way and then look at the coefficient. In this instance, there's a 1 here and a 1 here, a 4 and a 5. Recognize that if there's not a coefficient written, it's a 1. Okay, predict the products below. Anytime we're predicting products right now, we're going to have 2 salts, and we're going to follow the pattern of AB, CD, right? Becoming AD plus CB. The cation from here needs to end up with the anion, and the cation here, the cation here needs to end up with the anion over there. So AD would mean lead. Let's not use red because it's just hurting my eyes. AD would be lead iodide. We'll worry about charges and how they come together in a second. Right now, I just want to write down what the actual players are. CB is NO3. Oh, that's the B, so let's move it over. Our C is this potassium. I kind of wrote the CD under. There we go. Now that's more clear. Okay, but let's figure out in what proportions these elements will come together. Nitrate has a minus charge, and if there's 2 of them, I know this lead has a +2 charge. +2 charge, iodine always has a -1, so I'm going to need 2 iodines. Potassium has a +1, we already said nitrate. Or is this nitrite? Nitrate. Double check my polyatomic ions. Whatever this guy is, it has a minus charge, and so it comes together in a 1-to-1 with this potassium. The last thing we need to do is to show proper balancing and physical state. That means that I need to add a 2 to this Ki, to this potassium here. And are we balanced? 1 lead, 2 iodines, 2 potassiums. Okay, perfect. And lastly, I need to show physical state. Both of these were aqueous. This is soluble, so it's going to be aqueous. And this here is not soluble, so it's going to become a solid. We know this from rule number 3. We'll have to look through the solubility rules. Luckily, we have those on the exam. And in rule 3, we see that all iodides or iodine-containing compounds are soluble, except when compared with certain metals, one of which being lead. So lead iodide will not be solid. I should specify lead 2 iodide. Any lead iodide will not be soluble, but this particular compound is called lead 2 iodide. Okay, I tried to make this 6 big in so many different ways, but it just kept being small. And I really don't know why. What is the percent carbon in diethyl ether? Okay, if I want to know the percent of a certain element in a compound, I need to find my total molar mass. So let's identify, we're working with carbon, hydrogen, and oxygen. How many of each? I have 4 carbons, 10 hydrogens, 1 oxygen. And how much do they weigh? 12, 1, and 16. Okay, 4 times 12 is 48. This is 10, this is 16. Let's add these all together to find the total mass of this compound, of a mole of that compound, and it's going to equal 74. Now I just need to recognize how much carbon is making up the total. That's 48 over 74. Type that into your calculator, and it will tell you that this is 0.649, or we can say 64.9% carbon. Okay, 7. Which substance is the least conductive to electricity when dissolved in water? This question might seem like it's really difficult, right? I don't know how to recognize yet a compound and its conductivity. We haven't really talked about electricity that much. This question is really asking us, do you know strong acids and bases and weak acids and bases? And so it's important to recognize that some of these easy concepts that are just know it or you don't might be hidden behind a question that requires you to think a little bit. There's 2 parts to every chemistry question. The first part is, what am I being asked? And the second part is, do I know how to answer it? And so it might be either of those 2 parts that bring difficulty into the question. Obviously, in questions like this, and there's one similar to this on the review, the difficulty is identifying what this is asking me. So let's talk about what we're dealing with here. This is a polyatomic ion. It has a hydrogen on it. It's going to be an acid, and this is nitric acid because 8 goes to ic. Okay, so that means this is nitrate. I couldn't remember what this polyatomic ion is before. 8 goes to ic, nitric acid. Nitric acid, we remember, is strong. Okay, let's just identify what all of our players here are. Potassium hydroxide. Well, what does a base do, especially a strong base? Or, well, any base produces an OH, right? And these strong bases are soluble, we'll make an OH, so this is a strong base. Maybe we can label, this is a strong acid, this is a strong base. NH3, ammonia, this is what's on the end of our weak nitrogenous base, right? We saw it earlier, CH3, NH2, and so as we add that hydrogen element, it kind of goes back and forth between being an acid and a base, but no matter what it is, it's weak. HCl, hydrochloric acid, this is the acid everybody knows, and we should know that it's a strong acid. Okay, our question is asking us, which is the least conductive to electricity when dissolved in water? The more ions we produce, the more conductive we are. So this weak acid or base will produce the fewest amount of ions and will be the least conductive. If you didn't know that, you could have just thought about everything I know about these acids and bases and recognized I have a strong, strong, strong. My answer is probably the one weak. Okay, and the last problem. How many atoms of sodium are in 2 liters of 0.5 molar NaCl solution, or sodium chloride solution? Well, the first thing I'm going to do, molar means moles per liter. Now, I draw a long line, an equal sign, and identify where am I trying to go. I'm trying to know how many atoms of Na are in 2 liters of 0.5 molar NaCl solution. 2 liters of solution, I can go from liters to moles. I can do that because I'm given the molarity, and that's why it was helpful to write moles per liter right there. Maybe I should specify, this is moles of NaCl. moles of NaCl can become moles of Na. Maybe I should have made my line a little bit longer. And from moles of Na, we can identify how many atoms of Na we have. What's happening to my units? Liters, liters, moles of sodium chloride, moles of sodium chloride, moles of sodium, moles of sodium, sodium, and I'm ending in atoms of sodium, which is what I wanted for my answer. So my units look good. Let's fill in the numbers. Moles per liter, I'm going to need this expression. I have 0.5 moles for every 1 liter. For every mole of sodium chloride, I'm going to have a resulting mole of sodium as it dissociates in water. I know I'm in water because I have some sort of concentrated solution. And finally, I just need to remember the definition of a mole. 1 mole of anything, in this instance, a mole of the sodium atoms, is going to be 6.02 times 10 to the 23rd. We can put this in our calculator, or we can just recognize that we have 2 liters of something that's half a mole for every liter, so that we know we have 1 mole, or we have 6.02 times 10 to the 23rd atoms of sodium chloride. And there's our answer. One last quick note to make about this problem. Maybe you started it like this. You said, okay, I want to know atoms of sodium. Where to start? Oh, I know that this term here, this expression, means that I have 0.5 moles of sodium chloride for every 1 liter. You're not doomed to fail the problem. You're still starting in a correct place. There's multiple ways to solve the problem. So let's just make sure that we do it right. First, I'm going to start with the top and get rid of moles of sodium chloride. Where can I go that gets me closer to my answer? Probably to moles of sodium. And from moles of sodium to atoms of sodium. Great. Okay, I'm in atoms of sodium. I wanted atoms of sodium. I feel good. Let's check my units. Moles of sodium chloride, moles of sodium chloride, moles of sodium, atoms, atoms, except I have this term here that I never considered. So in order to make sure that cancels out, I need to put liters on top somewhere. Okay, well this makes sense because as I refer back to the question, I'm dealing with 2 liters of stuff. It wouldn't make sense to divide by that 2 liters, but it would make sense to multiply it since I have twice as much as I was considering before. And now liters cancels, moles of sodium cancels, moles of sodium chloride cancels, and I'm left with the proper answer. If you filled out the numbers, you get 1, 1, 1, 6.02 times 10 to the 23. And this is maybe even easier to see the math, that this 2 times that 0.5, we could just say it's 1 and 1, and the only real number we even had to deal with in this problem is the 6.02 times 10 to the 23rd, which was our answer. Hopefully that brought some clarification on these questions and kind of modeled the process of what type of thoughts should I have and questions should I ask myself as I approach different chemistry problems. If you're ever stuck, the best thing to think is, where am I going and where am I starting? And the rest you can just kind of solve from there, but identify what you need to know and what you've already been told, and that will help you out. So message me if you have any questions specifically, or just anything that you don't feel confident with going into the exam, and I'll respond as soon as I can. And thank you.